Hello and welcome to the first session of our workshop about CFD for green building design, organized in collaboration with the German Green Building Association, the Qatar Green Building Council, and SimScale. My name is Milad, and today I will guide you together with my dear fellow Muda through the content of our first session. And first of all, I would like to quickly introduce you to our today's lecturer. So Muda Youssef, he is the head of communication at the Qatar Green Building Council. He is a green building professional with a proven track record in green building and sustainable building, and at the Qatar Green Building Council, Muda coordinates different campaigns and projects related to sustainability-oriented design and building codes. And this and next week, Muda will share some very valuable knowledge with you about the fundamentals of green building design and how, for example, building codes are interacting with this topic. And my name is Milad. I'm the product marketing manager at SimScale. And as a part of my role at SimScale, I'm responsible for our relations and collaboration with other key partners like green building councils, other software vendors, and as a part of my role I also host workshops and e-learning courses on a regular basis. Yes, let's take a quick look at our today's agenda. So first of all, I would like to quickly discuss with you the idea of the workshop and to give you a quick outline about what you will learn this and next week. After that, Muda will introduce you to the fundamental concepts of passive design. And just after this, we will start to dive into the topic of fluid flow simulation and how it can be used in green building. Therefore, we will very quickly discuss some important theoretical aspects and fundamentals of fluid flow simulation. And after that, we will discuss how that can be incorporated for green building based on a real-world case study. And finally, we also have a Q&A session, so feel free to submit as many questions as you want using our question toolbox of GoToWebinar. And Muda and I will try to answer all of these questions at the end of this webinar session. Right, so let's quickly talk about this workshop and some organizational things. So to put it into a nutshell, the Qatar Green Building Council, the German Green Building Association, and SimScale joined forces to create this new workshop. And the idea is that we want to introduce green building professionals and students to the idea of fluid flow simulation, also called CFD. And we want to show you, first of all, how CFD can be used for green building projects. We will learn, and you will learn, how to understand when CFD can be useful and when not. And the idea is that during this course, you will also gain your first own hands-on experience with CFD. This workshop is made out of two sessions. The first session this week is about energy efficient design, and we will talk about natural ventilation and how natural ventilation can be improved using CFD. And next week's session is about thermal comfort, where we will more focus on HVAC design and how to improve thermal comfort, temperature distribution, and the flow field inside a closed room. And the great thing is that with attending the webinar, you will earn a 1 lead CE hour per session. So if you attend this webinar and the webinar next week, you will qualify for free lead CE hours, and we will also provide you with a short quiz for every session. If you submit both quizzes and 90% of your answers are correct, you will also receive a free professional training with a value of €500. Let's also quickly just go through some of the, let's say, most frequent asked questions. So first of all, yes, we are recording this webinar sessions, and after the webinar, I think tomorrow at lunchtime, we will send you an email including links to some useful resources to get started, link to the recording, and also to the quiz. It's just important for you to understand that you can only qualify for the lead CE hours if you attend the live webinar. And in the case you need support, we have our own dedicated user success team. And don't be shy, feel free to reach out to them by email, by phone. And we also have a forum where we have a lot of power users and also employees from SimScale who can help you quickly if you have questions or problems. And if you have problems with setting up a simulation, I would also ask you to use our forum where you will get help very quickly. All right, and I think we've now talked enough about organizational stuff. And I'm very happy to hand over the stage now to Muda. Muda, can you hear me? Are you ready?
Hi, Milad. Hi, everyone. Thanks for joining us today. Let me get that started on the screen, and we are. Let me show my screen. You can see my screen?
Yes.
Yes, okay. So hello, everyone. I'm Muda Youssef from the Qatar Green Building Council, and I'm glad to be joining you today with Milad and SimScale and the Green Building Association of Germany. So to get started, let's think of how do we deal with energy demand in building. Do we do it holistically or not? Can we manage it properly or not? So to take that answer, let's see how energy is being dealt in rating systems, specifically in LEED, as part of guidance to answer that question. So in LEED version 4 and same for LEED 2009, energy and atmosphere category is the largest and the biggest category in number of points. And it equates to 33 or 35, depends on the rating system percent. So 30+% of the rating system relies solely on the energy and demand, energy and atmosphere requirements. So it's a big emphasis and big highlight how energy plays a big role in designing and managing a green building. To take it further down, if we have a look further of what kind of topics are covered, for example, if we look at the LEED version 4 for new construction, we will find several topics being covered from there, from commissioning perspective, energy performance, refrigerant, optimizing energy metering, demand response, renewable energy production, green power and carbon offset, and so on. To summarize these topics or to group them together, we need first to highlight that you can't manage what you don't measure. So regard any strategies that you implement, any design principle that you want to deal with, you need to be able to measure it. So you'll be able to see if it can be successful or not. So it's part of setting a KPI or key performance indicators. And that will come in hand when later Milad show the case studies or the using energy simulation, and that's why do we need this kind of tools, because we need to be able to test and examine beforehand, before construction, how feasible or good our designs and how to measure these kind of decisions. So to group the topics, we have several topics to cover in energy and demand. Energy and atmosphere. So from energy demand, energy efficiency, renewable energy, and then in between to ensure your quality, you need commissioning and ongoing performance. Today we will only focus on the energy demand perspective and the principles of passive design for the sake of time, but maybe in the future we can further discuss other topics. So the intent overall is first, the reduction, why do you need to deal with energy demand as a first step, which is reducing energy use. Then you go for the next step, which is increasing energy efficiency. The later stage is how to meet the energy demand with clean renewable energy supplies. But keep in mind the order of application. We can't start by saying we will go for renewable energy without considering first the reduction in energy demand. It wouldn't be feasible, it wouldn't be a good choice to go the other way around. So the process, it's important to understand the cycle, the sequence, that first of all, we need to deal with how to minimize our energy demand. Then, sorry, so to go for increasing energy efficiency, and later on considering renewable and clean energy supplies. Of course, it needs to be an integrated process, an integrated approach. So whatever we're designing, we need to consider the construction and operation implications, and vice versa, how the operation can actually impact our design, and keep these kind of things in mind, and how all of that can be dealt with during construction. So speaking of design, we face lots of questions in design, from what and why and how to deliver our projects, why can we do this design and these principles, and what can be done with it. We have lots of challenges, not just the sustainability and environmental requirements, but you have lots of requirements from design side, client side, cost, even well-being and human well-being. Now it's more of a big concern, and people paying more attention to the human well-being, and lots of challenges that you need to balance and you need to achieve. So one of the very first things is, how can you integrate sustainability within your design framework? And for that, we have what we call the environmental design framework that we came up with a few years ago as a guideline for design. And it's part of it, or the starting pieces, is to integrate environmental aspects within your design guidelines. And then the environmental aspects, we will cover that later in the later slides. What are the environmental contexts that we need to consider? And then when you are evaluating your design alternatives, either it's a construction material or HVAC equipment or whatever, you need within your comparison matrix to consider a couple of things that are relevant to energy, like thermal gain, solar radiation, daylight efficiency, energy consumption, and so on. Of course, the matrix indicators can be bigger or smaller, depends on your project, but overall, keep the environmental aspects and indicators as part of your evaluation criteria. So it's not just cost, it's not just the design requirements, but also the environmental aspects. So having these in part in early design stages actually will save you lots of money. So it's good saving, and that's part of how to minimize the capital cost of going for green buildings, and actually maybe even do the other way around for capital savings. So as we mentioned, today we will be covering more of the reducing of the energy demand, but again, keep in mind the sequence. So starting with the reduction, going then for the using energy efficiently, then incorporating renewables. So our strategies that we will go through quickly in the next few minutes are a couple of passive design principles. From first one, which is establishing design and energy goals, optimizing building orientation, form and size, maximizing shading potential, using nature from daylight and ventilation, insulating efficient building envelope, and we need to highlight efficient building envelope, and then monitoring the consumption overall. Now we will go through each one of these strategies in the next few slides. So first thing, as we mentioned, you need to measure to be able to manage. That's part of the concept, that you need to understand your building typology and the average energy use intensity. Energy use intensity is the average energy consumption per square foot or square meter, depends on your region, per year. So it's either kilo BTU per square foot per year, or if you do the conversion, it will be kilowatt hour per square meter per year. So this is an average of energy use, and in each country, this is sourced from the US Energy Information Administration. You can have similar averages in your country, but keep in mind this is an average, and typically you shouldn't exceed the average if you're going for a green building. So that's something to understand, to speak early on with your design teams to understand what are the expectations of your buildings, what are we doing to achieve, and then put your EUI, or energy use intensity, as part of your design guidelines from day one. So keeping in mind what are the overall energy intensity, then setting the targets of the efficiency principles that you're going to achieve. Next principle is optimizing building orientation, form, and size. And for that, I can highlight or can speak more enough of how this is a very important, very crucial step. This is the keystone of everything that will come following. From understanding your context, as you mentioned, the environmental context, the principles of physics and geography, your wind direction, your solar sun path overall, and how to design in response to sun path and wind direction to passively cool or heat the space for maximum occupant comfort. And that's very important. Doing self-shading, doing building orientation, and that's something that you can now, using BIM software or using energy simulation software, you can easily test your concepts in early stages to see how they behave with different environmental considerations and climate zones. Again, part of it to consider how to utilize how to utilize nature, from using deciduous trees or using evergreen trees in different winter or summertime, moving air within the building, and doing it in response to other climate considerations. As we mentioned, during conceptual stage, lots of softwares, BIM softwares and others, you can evaluate your concept from an environmental perspective, from shading techniques, overall solar loads, and wind movement. And Milad will cover more of the CFD later in the stage. But doing that in the early stages will really save you lots of things, from the coordination costs and so on. And then typically within the simulation softwares, you will get what we call the optimum orientation, which based on your principles and your form will get you more of the how to position your building to best align it with your solar gains and air movement if you're going considering natural ventilation. Something to consider as well, how to utilize even shading techniques, from simple shading design. Again, all of these principles, what we call, are under the passive design techniques. So they don't have any mechanical aspects into it. They require almost zero maintenance. So it's something that it's at zero added cost if you take them into consideration from early design stages. Having the shadings, how to align them, using with your landscape, understanding the difference of path between the summer sun path and winter sun path, and so on. So to go through them quickly, from maximizing shading potentials, understanding calculating the angle for the summer solstice and winter solstice, and how to align your shading devices or shading features in the building to block the summer sun or to enable the winter sun. And that's the very basic principle. How to welcome it in the winter to bring more warmth into the space, and how to block it in the summer time to prevent it. Same thing, how to design for your inner courtyards to play with your heights, building heights, and the courtyard width, anyway, to prevent your summer sun, to be able to provide more shade and air comfort within the space. Using different trees for shading, or vertical passive shading devices, and vertical passive shading devices are more effective in your western and eastern facade. Your southern facade is, you can have more of a horizontal shader that work better on the southern facade. Again, you can use and test all of these principles using energy simulation tools, and now even from SketchUp to Revit and others, you can turn on the solar path and experiment different days in any hour or day per year based on your exact location, how the building will behave from a shade and shadow perspective. Other considerations to consider as well, from how to welcome daylight into the space. Now we have lots of studies and researches that highlight how it's important to welcome daylight into our spaces, especially in the commercial buildings, schools, and offices, and how they actually impact daylight, impact our productivity, well-being, and comfort, all the same. So we have different techniques to do that, from using different reflective materials or indirect skylights or solar tubes and solar diffusers and light shelves, all in all. Wind movement and natural ventilation, the making use of the difference between positive pressure and negative pressure, the very basic principle that colder air is heavier than warmer air. So these kind of principles, how to utilize them in the space, and we will see more of these in the later stage. Insulation, and that's for the efficient building envelope, and that's very important piece. Understanding how your building envelope thermal performance can behave, and you can use several softwares beforehand to identify the thickness of your insulation, how effective is your glazing, and so on. The idea from glazing is to permit the daylight and reflect as much as possible of the thermal load of prevented. Finally, something to consider as part of your building envelope is the principle of green roofs. Green roofs, it has different multiple benefits, not just to act as an excellent thermal insulator, but as well it has several synergies with other categories in rating system like LEED, when you deal with stormwater management, when you deal with providing open spaces, accessibility to access to the exterior, and wellness and well-being of the occupants to access and use these kind of spaces, in addition to water efficiency and rainwater capture and lots of things. So it has lots and lots of benefits that you can make use if you go for the green roof in your building. This is an example of a couple of passive design strategies that are applied in one project. That's from Share Properties project here in Doha. This project will house more than 100 LEED certifications upon completion in 20 hectares. So it's one of the largest LEED group of buildings in per hectare. As you can see in this picture, you have from light material for the roads, light colored and thick walls for the walls, even deep recessed windows, even if they are bigger in size, but you have several shading techniques using the landscaping for providing shades as well as part of the integration. So as we mentioned, and to sum up this part, it's important to understand that when we're dealing with energy demand, it's not an isolated topic, but it's need to be considered in a line with several other considerations, for example in LEED, and how to do it in regard with water efficiency, sustainable sites, building orientation, location transportation, and indoor environmental quality. So to summarize and sum up this part, we covered a couple of passive design principles, starting from establishing design and energy goals, optimizing building orientation, form and size, maximizing shading potentials, using nature from daylight and ventilation, insulating efficient building envelope, and finally monitoring consumption to be able to measure your success and your building performance. Thank you, and back to you, Milad.
Muda, thanks for the great presentation. Just give me 1 second to make me again the presentator. And in the case you have questions related to Hamuda's presentation, just write them into our question box and we will answer them during the Q&A. All right, so can you see my screen again?
Yes.
Perfect, so let's start. Yes, Muda gave us a great introduction to fundamentals of green building, and now let's first of all try to understand a little bit what simulation is actually is about, and therefore we will now quickly talk about the fundamentals of simulation. So what is simulation and what is CFD? Well, first of all, I have to say the term simulation is widely used for a different kind of tools. For example, building energy simulation also includes the term simulation. So what is simulation in general and what is CFD? Simulation in the end is nothing more or less than, let's say, a procedure or a tool which allows us to predict the behavior of a physical or technical system based on equations or mathematical relations we use to describe the problem. And CFD stands for computational fluid dynamics, and in the end it's a kind of virtual wind tunnel which allows you to virtually do any kind of fluid flow related testing. And what we actually do is that we incorporate numerical analysis or numerical approaches to simulate and solve problems involving fluid flows. And as I mentioned, these are some kind of virtual experiments, which means we are using computers to solve the equations. And the great thing about CFD obviously is that it allows us to virtually test a building or another product without the need to manufacture any kind of a prototype or a model. And it usually gives us a very fast and cost-effective insight into a flow problem, and not only explains what happens, but also why something is happening and why the flow field is behaving like it do. And just to bring some math into it, I don't want to go too much into this, but in the end of the day, when we use computational fluid dynamics, what we are doing is there is a couple of equations, a set of equations called the Navier-Stokes equation. And this equation describes the conservation of mass, momentum, and energy inside, let's say, a fluid. And the good news is we have an equation. The bad news is we cannot solve it analytically, which means this equation is, or these equations are so complex that there is no analytic way to solve them. And what we do instead is we transfer this analytic problem into an algebraic problem, which means we simplify it. And how do we simplify it? By using so-called control volumes. So instead of calculating the velocity and pressure field of our fluid flow for the infinite number of small points and the infinite number of time steps, we will only calculate velocity and pressure for so-called cells. So we are dividing our fluid domain into a lot of small cells, small elements, and for every of these cells we will get one velocity value or one velocity vector and one pressure value. And this is really great because it allows us to control the accuracy of our simulation. If we want to increase the accuracy, we will use more and smaller elements, and if we want to decrease the accuracy and also decrease the computational offer, we will use a coarser so-called mesh, so coarser cells. And that's, in the end of the day, the idea of CFD. So we, instead of analytically solving the equations, we will simplify the problem and numerically calculate the approximate solution for our fluid flow problem, which most of the time is accurate enough to be used for an optimization. And I mean, I think you now got a rough impression about how CFD is working, but why should you care about CFD? And for that, I would like to introduce you to an example, and you can find a picture now on the left side of the slide. And this picture shows the University Clinic in Aachen. It's a medical center. And the building was planned 40 years ago. And as you can imagine, for a hospital, ventilation is a very important aspect, because on the one hand, you want to make sure that there is a kind of thermal comfort for the patients. And on the other hand, you also need to make sure for example, that infection risk and the pollution, let's say, of bacteria, etc., is minimized. And back then, when they designed that hospital, simulation was not available at all. And when it came to the point where they had to design the HVAC system, they used the best practices and formulas and standards which were available. And in the end of the day, it came out that the whole HVAC ducting system was much underestimated. The problem was now that this ducting was integrated into the core of the building, which means it was not possible to increase further the diameter of the HVAC system by just replacing the ducts. And in the end, what they had to do, they had to build a complete new second HVAC system, which was like on the outside of the building, which you can see here now. And as you can imagine, this is not only not very aesthetical, it's also very expensive in terms of planning it again, building it again. Building this was much more expensive than building the first one, because as you can see, there was a lot of additional work which came with that, like building the support structures. And why I'm telling you this, because in the end of the day, simulation allows you to find a better design at an earlier stage, and that's why you should care about simulation. And in the end of the day, it depends from your perspective and on your focus, but you can use CFD to decrease costs by saving physical prototyping. And you can use CFD also to reduce the failure risk by, for example, validating experimental testing or assumption using CFD. You can use it to optimize the performance of your part by like testing different design approaches, for example, to reduce the pressure loss inside the ducting system, and so on and so on. And the great thing that it can be used or leveraged by basically everyone involved in the building design process. So architects can, for example, and designers can leverage it at a very early design stage to do some rough estimations about, let's say, the current state of the design. An engineer later can use simulation to optimize and validate designs before expensive physical testing. Yes, and I hope that this motivated you more to understand CFD. And now let's try to find out how we can use CFD for green building projects. And first of all, there are basically two major applications where I can use CFD for increasing energy efficiency of buildings. And it's basically both related to ventilation. And one thing I can simulate with CFD is natural ventilation, which we will also talk a little bit about in a couple of minutes. And whenever you have a building where you want to test natural ventilation, basically your model is made up out three, let's say, parts. First of all, you have the surrounding domain. Inside the surrounding domain, you have your building, which is a kind of hull with openings, and inside the building you have any kind of obstructions. And what is happening when we talk about natural ventilation? We have a, let's say, a global flow induced by the wind, which is going through our domain, and this flow field is interacting with the outer, let's say, surfaces, outer walls of our building, and a part of the flow is going into the building, interacting with the abstraction, and leaving the building again and going out into the domain. And now we have basically what we now need are boundary conditions. So there are basically three things we can do. First of all, we can like define and test different flow conditions. Like we can take a look at what will happen or how the natural ventilation inside the building will change depending on the wind speed, the wind direction, and the referral pressure. We can also use this for thermal simulation, and we have thermal conditions. And as you know, for natural ventilation, I need heat, and we can define thermal boundary conditions like temperature, heat generation, and heat transfer. And I think this is something where we need to make some clarification. So temperature means I define a fixed temperature, for example, for a wall. Heat generation, so what I'm interested in is the temperature of surface in Kelvin. Heat generation means how much heat energy is released. And usually this is a volume source. This could be, for example, let's say I don't want to say a fire, but a fire is a pretty good example for heat generation, or a lamp, for example. If you have a lamp which is bringing radiation, this is heat generation. And we have heat transfer, where we not define, let's say, the temperature, but we define the heat transfer coefficient between the air and the wall. This is usually used, for example, if I want to test different insulations, different, let's say, window types. And I can also do passive scalar analysis when I want, for example, to trace how particles are bring into the building or removed from the building. And for example, everywhere you have a lot of sand. This can be important because you have a natural insulation concept and you want fresh air in, but you don't want that this fresh air takes sand into the building. And now let's talk about how we can use CFD for green building. And as you know, when it comes to green building, a very important point is certification and sticking to standards. And the great thing is that, let's start with the bad news. Unfortunately, in the past, when most of the standards were developed for the first time, simulation was not an industrial relevant tool. But there are some standards already where you can apply CFD, and including the ASHRAE standard 55 for thermal comfort, the ASHRAE standard 62.1 for ventilation. And the great thing is that the ASHRAE, the Green Building Councils, joined forces and developed a new standard called standard 189.1. And this standard will be a unique standard combining all the standards for green building. It will be the, let's say, the first standard tailored really to the needs of green building. And the great thing is that in this standard, simulation will be much more incorporated. So let's give you some examples where you can apply CFD in accordance with the standard. And for example, thermal comfort, as I mentioned, ASHRAE standard 55, basically is a very good example for the strength of CFD, because if you think about it, when it comes to thermal comfort, you're interested in what is happening, let's say, inside the room from a local perspective. And all the other tools we have, like building energy simulation or hand calculations, just give us one temperature value and one velocity value for the whole room. And in contrast to that, CFD is able to really show us detail where we can expect which temperatures and which flow conditions. This is something we'll talk about next week. Then, for example, ventilation for acceptable indoor quality, which is part of ASHRAE standard 62.1, can also be very quickly are very easily used together with CFD. And this is, by the way, what we'll show you today. And also energy consumption and efficiency can also be improved and proved also with the use of CFD. However, there will still be some parts of the standards which cannot be considered with CFD. And in the end of the day, whenever you are not sure if you can use CFD, just try to get the physical perspective. For example, for water usage, for site system, also surface finish. These are all things which are accounting, let's say, into the rating of the building, but they are not related, let's say, directly to any fluid mechanics, and therefore it makes no sense to use CFD there. For example, for the water usage mainly depends on the number of persons inside the room and not on the design of the water supply system, and that's very important. Not everything can be simulated, but what can be simulated usually is very sensible and meaningful to do it with CFD. And now I think we had a lot of theory, And now let's try to gain some practice. And therefore we have prepared a live demonstration for you, which is about natural ventilation. So let's start. First of all, why is ventilation so important in modern building design? And as you might know, and I think Muda also explains this, building a residential building is one of the biggest producers of climate gases and uses most of the energy. And especially if you take a look, and this is a good example, this was a study performed by the US Energy Administration about the energy use in US commercial buildings, and you can see 25% is used for heating and still 10% for ventilation, which is a lot. And it's really the building sector is the biggest single contributor to world energy consumption, and therefore optimizing heating or ventilation can help a lot to reduce the overall energy consumption of buildings. And as you know, natural ventilation is something that we can leverage for this purpose. So, and what is natural ventilation? The idea of natural ventilation is that I have that I don't need to force the air exchange, for example, by using pumps or impellers, but that I can force air exchange by taking advantage of physical properties of air. And natural ventilation, in contrast to forced ventilation, means that the flow is induced by a temperature gradient inside my fluid flow domain. Just to give you an example, if a gas gets heated, the density drops. When the density drops, I get lift, and the hot air rises up. And that's basically the chimney effect. And we can now try to leverage this effect to ventilate a building without using any energy at all. And it has a lot of advantages. First of all, we have no or very low costs for moving the air through the building. And this for sure means that we have reduced total energy use. It's more comfortable because usually it's without any noise. It's much smoother usually, so you don't have such a strong draft, but it also has some disadvantages. First of all, it's not possible everywhere because you need an average enough wind, and you also need to make sure that the openings, because you cannot build any filters in between, or it's hard to build in between, that the other external conditions of your building or of your project allowing to do it, like that you don't have any noise outside, or if the building is in the middle of the desert, it's also questionable if it's really smart to do natural ventilation. And for sure you have lower control, and that's maybe the biggest issue, because you cannot control the wind speed. And if you think about it, if the wind speed is like just 50% of what you're usually expecting to, at least your ventilation rate will also drop by around 50%. So natural ventilation is very powerful, but you need to make sure that it works. And now let's take a look at the standards I mentioned. And when it comes to natural ventilation, there are two things we're interested in. First of all, the airspeed inside the building, because you all need this bad feeling that you have when you are like standing, let's say, in drafting air. And this is what the AirSpray standard 55 is about. So the standard says that the interior airspeed should not exceed 0.2 meters per second. And for some cases, you can extend this criteria to 0.8 meter per second. But however, you should not go above that, because this will create a lot of discomfort. And the next thing is that you need a certain air exchange rate. And the air exchange rate is basically defined, it's a product of the mass flow or the volume flow, which is going into your building, divided by the volume of the building itself. And these two things are contrary, because if you want a high air exchange, you need high volume flow, so high airspeed, but this will create draft, and so it's a kind of chicken of egg problem which you need to optimize at the same time. otherwise you will get in trouble. And this is again a good example why CFD can be so helpful, because without CFD it's quite hard to make sure your concept is working without building a physical prototype. So today we're going to take a look at a simulation which is also available in our public simulation library, and it's a small warehouse, a small shopping mall, where we want to validate the effectiveness of wind validation. And as you can see, we have different levels and a lot of windows, and what we want to do is to find out which window configuration will lead to which kind of air exchange rate and to which, let's say, a level of thermal comfort. Yes. And I talked a lot with you about simulation, what it does, but I don't share it with you what we guys at SimScale are doing. So just to keep it quick. We are a startup company. We were founded as a spin-off of the Technical University of Munich, and our vision was to make CFD accessible to everyone. And the reason is that it wasn't in the past. So in the past, only 1 to 3% of engineers had access to simulation. And we wanted to reinvent the way simulation is used. And SimScale is basically the world's first web and cloud-based simulation platform where you can register yourself and set up, run and analyze the simulation results in 3D in your web browser. And the great thing is you don't need to install any software, you just need a web browser. You don't need any dedicated hardware software because the software as well as the computing power is coming from the cloud. And the tool was designed really for everyone. So it's not another tool made for simulation experts, but a tool for engineers and designers who wants to leverage it. And basically you can use CFD for a lot of applications in green building and AEC. For example, we will take a look today at thermal comfort, but you can also use it for contamination control, for example, to improve the ventilation concept of a parking garage, and you can also use it for example, pedestrian comfort analysis in larger arrays of big buildings, also for wind load analysis. And this is the scenario we will take a look at today. So this is our building and we have 4 configurations. And at the first configuration, only the first floor windows, the ground floor windows are opened. At the second configuration, the first floor windows are opened. At the third configuration, the second floor windows are open. At the fourth configuration, all windows are open in all floors. And now let's quickly switch to the SimScale platform, because I've prepared something for you. If you go on simscale.com and you go to public projects, you can just, here you will find thousands of ready-to-use simulation projects, including the CAD model, the simulation setup, and the results, which you can import to your own dashboard quite quickly. And I will just look for natural ventilation. And instantly I can see a project which was prepared by my colleague Pavel. And this is a project we want to take a look at now. And let's open it. And as you can see, everything I'm doing now, I'm doing it in the web browser. Okay, and first of all, you can see the CAD model of the building. And very important, since we are interested in the flow inside the building, it's very important, we need to have a proper model. And in this case, there are 2 possibilities. One is to extract the internal fluid domain, or the other is to take a solid model and define a kind of wind tunnel around it. Okay, and you can see we have uploaded all the geometries. You can play around with it, and the next step is to create a mesh. And this is a process I mentioned at the beginning, which is about transferring our continuous problem into a discrete problem. And so this is our fluid domain. And for example, I can now take a look inside the mesh, height faces. Yeah, now you can see like this is our outer domain, this is a building, and for every of this hexaeders we'll calculate one pressure and one velocity value. All right, so let's continue. The first thing we need to do is meshing, so we need to define our geometry. And here it's very important to use the right mesh size at the right place of the model. And don't forget that in the end of the day, as smaller these elements are, as more accurate is the simulation, and therefore in the near of objects with sharp edges, we use smaller elements, and away from the building we used larger elements. And what we actually did, we defined one overall mesh size and some refinements. So we refined some of the surfaces, some of the regions, some features and edges. And in the end, this resulted in a 5.1 million cells volume mesh, which means we will calculate velocity, pressure, temperature, and all the other stuff for 5.1 million points. And that's what we did. So let's take a look at the results. And what we can see now is the visualization of the velocity distribution at the head level inside the ground floor for all 4 different configurations. And what we can directly see is that, and don't forget, so the scale is that was like this, at 0.8 is the transition from dark blue to cyan. So everything which is dark blue is fine, and then it becomes critical. Here you can see that basically for all configurations you have like a long axial with a very strong draft. And since this is like the main corridor of the building, here you will have a lot of discomfort, and this is something you need to think about. And actually this is also something you cannot really solve, because here you have the entrance with which is open all the time. And if you take a look, I mean, if you open more windows, the only thing which happens is that actually the discomforts increase, and this axial gets a little bit banded around the z-axis, but that's it. If we now take a look at a little bit higher slice, so it's the first floor on head level, we can see that actually the problem is I don't want to say it's solved, but here actually everywhere we have a high comfort, except for, and even if the window on this floor are opened, just in the near of the windows we have a small draft, but actually it's looking fine. And only if all the windows are open, it seems like we become some small areas in the near of the stairways where the velocity of the air is quite high and it's quite discomfortable. And we can do the same for the second floor, and actually here you can see that at the second floor for all configurations it's pretty good in terms of comfort and wind speed. And actually what is happening that is quite funny, if you take a look, if you take a look back at our different configurations, the windows are just opened a little bit, while the entrance door is completely open. And this seems to be the first big problem, that we need to find a way to manage or to reduce the mass flow coming in from the door. And we can also create slices in another direction. And this is basically now a slice which is following the stairway. And here you can see again that actually the big draft is directly coming in through the entrance door, and we have some recirculation here. And especially if like only the windows on the ground floor are opened, this creates a strong draft because it's directly going through the room. And if you open the windows on the first level, you can see that we still have this axial, but it's a little bit smaller. And if we then even open only the windows on the last level, last ground, it's like still changing. However, it seems like this ASIL in the middle is a big problem. And therefore, let's take a look at the Isosurfaces, which is another visualization type. And Isosurfaces means that we're connecting all the points with a defined value for velocity. And this is 1.8 meter, and you can really see this, the enclosed volume is a region of incomfort. And so you would need to, in the end, it's just ASIL this part, and you need to find a way to reduce the flow velocity here. What we also did, we calculated based on the ASHRAE standard and simulation results, we will be able to calculate the air exchange rate and the volume flow. Yes, and this can also be used to further incorporate our design. So, and I hope the demo showed you that the wind ventilation is really significantly affected by the airflow within the building. And here the big challenge is that using windows only on one side of the building does not provide a sufficient air exchange. And on the other hand, this wind ventilation induced air circulations inside the building, which might cause too fast air motion. And the biggest problem here is that the door is open all the time, and it will create a lot of discomfort at the bottom floor. And here it will be necessary to installing wind obstacles to reduce the level of discomfort. All right, thank you very much for your attention, and I think we are really on time. And if you have any questions, please feel free to write them now, or you can also reach out to me by email if you have a question, and we will discuss it next week. All right, seems like all questions were answered. Yes, I would like to thank you very much for joining us. And also thank you very much, Muda, for being here with us. And yes, I'm looking forward to next week. And yes, have a lot of, I hope you had some fun. And tomorrow we will, oh, there's some question. Tomorrow we will send you all the resources. Some people ask how they can get the software. You just need to go on simscale.com. There you can create your own free account and directly start to simulate. But we will also share this information with you by email tomorrow. And we will also send you a link where you can import the project I showed you to your own workspace. Yes. All right. Thank you very much. Have a nice evening. See you soon. Bye.